Hello, my name is Adam Kollin. I'm president of RHK Technology. I know many of you that are logged in. Some of you I don't know, so welcome to the newcomers. We appreciate your time, taking time to join us for today's R9 webinar. We're really proud to share with you our new flagship product, the R9. As you'll see, RHK has invested many man-years in the development of a truly unique control system that can help take your research to new heights. Part of the theme of this webinar will be to show how the R9 has developed to meet the goals that seem contradictory and even impossible. How to simultaneously be easy to use, easy to customize, but easy to use. How you can simultaneously have extremely wide bandwidth, but also extremely low noise. Be good for both experts as well as beginning users. If you have any questions as I go along, please type them into the box on your webinar control. I'll try to get to as many as I can at the end. If we run out of time, I'll follow up with you personally to make sure that your questions get answered. Many people know RHK by the SPM control systems that we've been making for many years. However, RHK is much more than a controller company. We've sold hundreds of STMs and AFM microscopes, primarily for the UHV and cryogenic markets. RHK offers many market-leading products. Our quadruprobe cryogenic 4-probe microscope provides the highest resolution integrated SEM, along with unique capabilities such as integrated microwave and near-field optics, as well as atomic resolution on each of the 4 STM probes. Our flagship microscope for many years, based on the Beetle design, is very well known for its extremely low thermal drift and high stability. Our line of cryogenic microscopes are based on the remarkable designs of Dr. Shuhong Pan. These microscopes are available as just a scan head for integration into your own existing cryostat, up to complete cryogenic microscope systems, including with a closed-cycle helium refrigerator. RHK's newest products include our line of near-field optical microscopes. This line includes both tip-enhanced Raman microscopes, as well as ensoms designed for both visible and infrared light. We have systems designs for both ambient conditions, as well as for vacuum and cryogenic operation. But today, we'll be focusing on our R9 control system. To fully understand the R9 controller, it's useful to understand its heritage. RHK launched the first generation STM 1000 way back in 1988. This was the first commercially available STM control system. The STM 1000 was an instant hit. The availability of a commercial control system brought many researchers into the new field of nanotechnology. As the field of STM branched out and many different types of SPMs were developed, the STM controller grew into a SPM control system and evolved to support the new fields of research. RHK worked with many of the leading research groups to incorporate the latest features and capabilities that were required to keep on the leading edge of research. The SPM 1000 came to be the standard control system for many of the top research labs around the world. When a researcher said they had an RHK blue box, their colleagues all knew what they were talking about. One of the leading features of the SPM 1000 was its wide range of capabilities and ability to interface to any microscope design. Many researchers would modify the SPM 1000 to add their own unique capabilities. The SPM 1000 helped enable many of the breakthroughs in nanoscience that are now taken for granted. After more than 20 years of continuous evolution, the SPM 1000's basic architecture had reached the end of its life. It was clear that we needed to reinvent the field that we had helped establish if we were going to continue to provide innovation at an even higher level of enabling technology. In 2008, we gathered together at RHK 8 of the leading researchers in their fields of SPM research. We posed a question to them. If you could have your dream controller, what features and capabilities would you wish for? What features and capability is currently limiting what you're able to study? It was an exciting weekend. It's really fun to be able to dream about what can be, especially when you're surrounded by such great minds. Working together, great new ideas just feed off of each other. With the input from our technical advisory board, we took everything that we'd learned over the previous 20 years and started working on our new dream machine. Starting with our core team of electrical engineers that had been with RHK from the beginning, we expanded our development team to 10 people. After almost 3 years of hard work, we were finally able to bring the R9 to life. Our team was not tasked with just developing another controller. Our goal was perfection. We strived to develop a controller that inherited the strengths of the SPM 1000, but with a cutting-edge architecture and capabilities that would keep the R9 going strong for another 20 years. But how do you do that? First, we decided that 100% of the R9 had to be developed by RHK. From our experience with the SPM 1000, we knew we could not rely on boards made by other companies. We knew that to achieve perfection, we needed complete control over every circuit, every driver, every component in the R9. To keep the noise levels to the theoretical minimum, we designed every board in-house. Our engineers used every lesson and every trick that they'd learned over 20 years to guarantee that the R9 would maintain the tight specifications that we'd established for it. The R9 was truly a technological triumph. The R9 tightly integrated many high-speed components. We have over 30 ADCs and DACs directly connected to extremely large FPGA chips. Much of the magic of modern controls is due to the capability of the firmware you develop for the FPGAs. Only by having full control of this firmware can you truly harness the full potential of your system. We have over 10 man-years of engineering just in the firmware development of the single FPGA chip. To complete the R9, we knew that we needed to incorporate a linear power supply as we had done with the 8 generations of SPM 1000. These linear power supplies are heavy and expensive, but they're the only way to maintain the low noise levels that RHK is famous for. Without the high-frequency noise of switching power supplies, we did not need to filter out all the high-frequency signals coming from the microscope. So what does all of this advanced technology mean for you? Technology is useless if it does not provide a clear benefit to the user. One of the most useful benefits of the R9 is the increased dynamic range of operation. While this can sometimes be a little hard to illustrate, a wide dynamic range just makes all measurements easier. A wide dynamic range allows optimal performance without the need to frequently fine-tune operating parameters. It allows beginning users to get quality results without the steep learning curve of understanding the function of each control. This improvement is most obvious when upgrading from an older generation controller. There is no longer any need to ever adjust the A to D gain, the Z offset, the slope compensation to get the highest resolution images. You maintain the highest resolution regardless of offsets and slopes. Also gone are the days when you need to scale the high voltage outputs to allow atomic resolution images. The need to adjust the red box and yellow box of the SPM 1000 was eliminated with the R9. A fully integrated system provides countless benefits. Gone are the days of multiple separate boxes for separate functions interconnected with a web of cables. A single click of a mouse can completely reconfigure the R9 to perform wildly different experiments. The noise floor of the R9 is far below that of other parts of the SPM experiment. The R9 will never be the limiting factor in your lab setup. RHK's unique multi-speed data paths allow sensitive measurements of low-level signals with the simultaneous acquisition of extremely high-speed transients. Other control systems lose the high-frequency information when they filter out their high-frequency noise. RHK's unique time-based data acquisition allows a deeper investigation into your data than is possible with controllers that discard the raw data once it's been averaged into pixels. The tight integration of all hardware components and RHK-developed firmware enables rapid response to changing input signals. During atomic manipulation, Ramping a bias voltage can be shut off within a few microseconds when a threshold is reached. Control systems that must labor under layers of LabVIEW can take milliseconds or more to respond to these changing signals. RHK has a perfect combination of ease of use for beginners with the ability to be customized and enhanced by advanced users. As previously pointed out, the benefits of an integrated system are many. Noise is reduced due to far less interconnecting cables. Most signals are handled in the digital domain, eliminating the noise from the redundant analog circuitry. And what researcher hasn't lost time due to an incorrectly connected cable or spent hours trying to track down an intermittent connection? That is all a thing of the past with the R9. One example of the advantage of the R9 approach can be seen in the configuration required to make DI/DV measurements. With the R9 having the lock-ins fully integrated, it can be seen that the analog signal from the preamp is only digitized once. From that point, the signal travels through the R9 as digital data. This digital data feeds the feedback loop in both lock-in amplifiers. All the signals, including the current, topography, and the lock-in signals, maintain their full 32-bit precision and are stored directly without ever having been converted back to analog signals. In contrast, other control systems which require the use of an external lock-in amplifier, the data undergoes numerous conversions from analog from the preamp to digital, then back to analog, then back to digital, before finally being imaged and stored. In addition to the noise generated by the extra cables and connections and the lack of reliability, much precision is lost in the needless data conversions. I'm now going to go into some detail to show off some of the unique capabilities of the electronic circuitry of the R9. Electronic design and board-level integration has long been one of the core strengths of RHK. It is not difficult for a company to just build a circuit board that contains a lot of analog and digital circuitry. However, it is much more challenging to design a product so each component will work optimally and perform to full specifications as a system. This is an area where RHK's industry-leading experience has really paid off. The probe interface board set that is shown contains most of the ADCs and DACs that interface to the microscope. These ADCs and DACs are all directly connected to a very large-scale FPGA chip that handles most of the functions of the controller. Many people are familiar with DSP technology, which was common in previous generation controllers. Where a DSP could handle a string of tasks at a high speed, they were serial devices and could only handle one calculation at a time. FPGA technology, on the other hand, is inherently parallel, so they can process many tasks simultaneously. FPGA has largely replaced DSP technology in advanced instruments. Many of the advanced tasks, such as the oversampling of the input and output data, must operate at the full 100 megahertz data rate of the data converters. This is easily handled without causing any delays in other parts of the FPGA chip. Integrating the signal generators, lock-in amplifiers, and PLLs onto the same IC provides the ability to exactly lock the phase of these signals to a precision that is just impossible with separate instruments. It also enables multiple harmonics and sidebands to be precisely synchronized. The R9 contains a variety of different ADCs and DACs that are selected according to the application where they'll be used. Each R9 has two ultra-high-speed input channels. These are the main inputs that would normally be connected to the tunnel current for an STM or for the normal and lateral force signals in an AFM. Each of these channels has a bandwidth of almost 20 megahertz. It is RHK's philosophy that as much of the original data should be preserved as possible to allow the researcher the ability to dig deeply into the raw data to try to achieve a deeper understanding of the system under study. Many companies heavily filter the raw data down to just a few kilohertz before it's digitized to mask a high noise floor or artifacts generated by poor circuit design or noise coming from the switching power supplies. Filtering out high-frequency noise also unfortunately filters out your high-frequency data. We do not feel it's our job to decide if you should only have access to the filtered data. If you want to filter your data, you can always do that after the data is acquired. In addition to a high bandwidth, these input channels provide programmable gain to allow even the smallest signals to be accurately measured. Even with the gain set to its maximum value of 512, the input bandwidth remains undiminished. These input channels also have programmable input offsets, which allow offsets in the input circuitry or from the preamplifiers to be nulled down to exactly 0. In the past, you often needed to stand on a ladder and adjust the offset of the preamp with a screwdriver. These high-speed channels allow the selection of standard BNC inputs or impedance-matched differential inputs that connect to our matching preamplifiers. These differential inputs provide optimal performance for low-level and high-frequency signals. Due to the magic of oversampling, the dynamic range of these input channels can be as high as 24 bits, even with a relatively wide bandwidth. We utilize highly sophisticated algorithms that provide significantly superior performance compared to typical averaging algorithms. And all of the sophistication does not come at the expense of low noise. The noise floor of the R9 will never be a limitation of your experiment. Here you see a noise level down around 6 nanovolts with the graph going to 5 kilohertz. If you expand this graph out, you see the flat noise level extending all the way out to 20 megahertz. One of the truly unique capabilities of the R9 is the ability to have such low noise and resolution while maintaining extremely wide bandwidth and timing resolution. Our transient recorder, which runs in parallel to our low noise data pathway, allows high-speed information to be measured with up to 10 nanoseconds precision. In the example shown, the tunnel current is displayed in the last couple of milliseconds before and after the tip has approached the sample. In the first graph, you see the current spike a few times before the feedback loop has had a chance to regulate. Normally, this probably would result in a crash, and the only way that you would know it is if you saw a hole in the middle of your sample. This transient would be impossible to see with other systems, as the high-frequency data lasting less than a millisecond would have already been filtered out before it was even measured. With the knowledge of the first measurement, the feedback parameters can be adjusted to prevent those tip crashes on approach. With the R9 system, every time you approach with an R9, this graph will pop up automatically to display the input signal at the final moments of approach. If your input signal is from an oscillating probe, such as a cantilever or tuning fork, the graph will display the actual individual oscillations of the probe, and not just a low-frequency amplitude signal from your lock-in or PLL. Complementing the two ultra-high-speed input channels are two ultra-high-speed output channels. These outputs are typically used for the bias voltage in STM and the probe drive for AFM. The oversampling in the outputs again provides an amazing dynamic range. The output can range continuously from microvolts to volts and from DC to 20 megahertz. The graph on the right shows a 5 microvolt AC modulation superimposed on 25 microvolt steps as may be used in very careful spectroscopic measurements. This signal is directly digitally generated and does not require external attenuators or analog mixers as required by other control systems, including that of our own SPM 1000. In addition to the two ultra-high-speed inputs and outputs, the R9 contains many other input and output possibilities. There are two additional high-speed input channels that provide both programmable gain and offset capabilities. 5 more ADC input channels are available with fixed input gains. All of these channels can be acquired simultaneously, along with the dozens of internally computed signals, such as that from the internal lock-ins in PLL. Six additional DAC channels are available, which are easily software configured for any customer requirement. The piezo interface board contains another 12 DACs that are designed to interface to the scanning system of your microscope. For optimal noise performance, 8 of the DACs are directly connected to high voltage amplifiers for use in driving the piezo elements of the microscope. No external BNC cables are required to go from the output DACs to a separate amplifier module. Each DAC is software configurable so they can be optimized for any type of microscope design. An additional 4 DACs are provided with low voltage outputs. These are provided to interface to a scan stage that is an integrated power supply. 4 ADC inputs are provided for reading a scanning stage's position sensor to allow for closed-loop operation. It's not likely that anyone will use all of these capabilities at once, but as your experiment grows in sophistication, it's good to know that your controller will not limit what you can dream to explore. Here is a comment that we received from one of our customers in China that's had his system for about a year and a half. He placed an order for a second R9 just last week. Dr. Joe makes many different microscopes of different configurations and rather unusual configurations of how the voltages are applied to the piezos. And he's someone that takes very good use of the flexibility of the R9. This slide graphically displays the enhanced capability provided by our multi-speed data paths. As the data is digitized at the 100 megahertz rate, it flows into 3 separate parallel paths. The top path flows into our transient recorder's ring buffer. We are always filling this data buffer, and its contents can be grabbed at any time. You can just push a button to grab it at any random time, or the procedures can be selected to trigger at a specific time, such as the final moment of approach. The recorder can be configured to provide the data that's acquired after the trigger, the data that occurred before the trigger, or in the case as this graph shows, for a few milliseconds before and after the trigger. The full 100 megahertz data stream also flows to the PLL and lock-ins. This allows signals in higher harmonics up to 20 megahertz to be demodulated. The final data path flows into our digital filters, which slow the signal down to a 200 kilohertz rate while increasing its resolution up to 24 bits. Contrast this with the limitations of other controllers. As their input data is heavily filtered before it's even digitized, all high-frequency information is permanently lost. One of the unique design concepts of the R9 is our method of data acquisition. Since the time of the first STMs were developed, most researchers have dealt with their data as pixels. Although this is a convenient way to visualize data, everyone knows the world is not made out of pixels. The real world is analog. Real information can be lost when converting from an analog input signal to pixels. RHK looks at an SPM experiment as a constantly changing interaction between a probe and sample with various sources of excitation and various channels of responding signals. A standard control system will produce an image such as that is shown on the left. When you see a pixel that appears out of place, you can only guess what happened. There were probably many readings that were taken during the scan that were averaged together to make that pixel, but they were averaged together to generate the pixel and then discarded. That information is now permanently lost. The R9, on the other hand, keeps this raw data in a separate file so you can go back at any time and examine it if you later decide that you need a deeper understanding of your measurement. Changes to parameters are also kept during the measurement, so you'll always know exactly where and when the parameters changed. In the example on the right, the R9 will display that the bias voltage has changed at that pixel location and that the current and topographic signals spiked in response. The R9 sends a continuous stream of data to the host PC, along with the normal channels of data such as topography, current, force, dissipation, or other channels that include sync markers that show when a scan started and stopped, which data is topographic and which data is spectroscopic. The software uses these markers to parse the data into real-time image and spectroscopic curves. The excitation markers represent a change in parameters such as the bias voltage, the scan speed, the feedback set point, the oscillation amplitude, or or frequency, they're inserted into the data stream to allow an exact correlation of the excitation and response signals. Data is collected during the entire experiment, including when the tip is moving to the origin of the scan or when the tip is moving down the y-axis. This data is not displayed in a standard pixel image, but is available for examination if you're trying to gain a deeper understanding of your data. Maybe the problem is the data changed significantly between scan lines, and you want to see if something happened while the tip is moving in the slow scan direction. This data is simply not measured with other control systems. Although this raw data is rarely examined, we don't see it as our job to throw away your raw data. This slide shows how parameter changes are displayed on the data. In this example, the Z feedback loop was decreased in steps and then returned in steps back to the original value. At each parameter change, a dot is displayed on the image showing exactly where that change was made. When you move the mouse over a dot, a box will pop up and show the changed parameter. Here you can clearly see when and where the feedback loop was changed and the effect it had on the image. Every other system requires the student remember to write these changes down in their lab notebook. But even if they're diligent and follow their instructions to keep track of what they've done, they can never precisely show where on the image those changes took effect. R9's time-based data acquisition can be even more useful for spectroscopic measurements. The data stream for the various channels of data is acquired continuously during an experiment. It's not interrupted between the topographic and spectroscopic portions of the measurements. With the R9 controller, in addition to seeing the data as a single data point at each bias voltage step, as you would see with any other control system, you can dig deeper. You can visualize the current after you stop scanning and before you open the feedback loop. You can visualize the current as the bias voltage is ramped to the starting value of the IV curve. You can visualize the amount of overshoot at each step. You can see individual readings at each step. All of this information can provide new insights into your experiment. It's also an excellent tool to help optimize the various settings of the measurement. Other controllers turn off their data acquisition during these phases of the measurement and throw away the raw data after it's averaged for display. Spectroscopy is one of the features that the R9 customers are really becoming very appreciative of. Here's a comment from one of our customers in China. At the Chinese Academy of Sciences, they now have, I think, 6 R9s. And this has now become the standard control system for precision spectroscopy measurements. I'm now going to show how an advanced user can quickly and easily customize their R9 to perform new and novel experiments. I need to stress that these steps are not required for the average user. When I give a presentation on the controller, sometimes I'm a little afraid to even show this. Half the customers look at it, their eyes get big, and they're very excited with all the new possibilities. The other half of the group looks at it and thinks, oh my goodness, look at all the new things that I have to learn. Well, the good news is most people don't really even have to learn this. When you buy an R9, it comes fully configured to interface to your microscope. If you never reconfigure your microscope, you may never even see these configuration screens. But the power and flexibility is always available if you need it. The R9 hardware is configured by our IHDL, which stands for Iconic Hardware Description Language. You have a long list of real and virtual components to choose from. The real components include ADCs, DACs, high voltage amplifiers, digital I/O, and so forth. There are also virtual components which include PLLs and lock-ins, feedback loops, scan generators, along with a variety of other support devices. We've got lots of feedback loops available inside of the R9. So for customers that had an AFM that need a feedback loop for the Z topography, to do Kelvin force microscopy, for feedback off an interferometer for a quadrature lock, These can all be done simultaneously. To configure the controller, you simply select the components that are required and graphically connect them together. It's that easy. This example shows the setup of a basic STM. There are, of course, some basic rules that must be followed, but if you make a mistake, the software will alert you, show you what you did wrong, and not let you continue until you fix the mistake. This is an example of a more complicated configuration for a TERS microscope. You can have a different configuration file for different microscopes, or for different experiments, or even for different users. Switching between any configuration is simply the matter of selecting the appropriate file. In one configuration, you may image the output of a lock-in amplifier. In the next configuration, you might feed back off of the output of that lock-in. The R9 eliminates the confusion and mistakes that frequently occur when reconfiguring an experiment. Here is a comment from Professor Shui and Professor Chang at Tsinghua University that take full advantage of the flexibility of the R9 system to optimize it to exactly meet their experimental requirements. I'm now going to switch over to my other monitor. Everything that I showed you up till now shows you how the system is configured and what are the individual components. However, now I'm going to show you the actual software and how you'd interact with the software on a daily basis. We've organized the system so the controls that you use frequently are readily available, intuitive to use, and easy to understand. Many people liked our old SPM 1000 since the analog knobs gave you a really unique feeling of control over the parameter settings. It allowed you to make small changes to the bias if you just turned the knob a little to add just a few millivolts, as well as large changes by just turning the knob a bigger amount or faster. With the R9 system, we wanted people to still enjoy the look and feel, though with digital controls. We invested a lot of time to give our users a fast and convenient way to do this. To change a value such as the bias, you click the mouse into the bias setting box. You then use the left and right arrow keys to select which digit you want to change. If you want to change by 1/10 of a volt, you move the cursor into the 1/10 of a volt column. If you want to change by a smaller amount, like millivolts, you move to the millivolt, and then use the up and down arrow to change that. You can also just type the number in. So we give you the ability to change very precisely and very accurately. With the SPM 1000, you could change how fast the control changed by how fast you turn the knob. Well, we don't have knobs in the R9, but we do make it very easy for you to control how fast a value is changed. Almost every value that can be changed in the R9 has a parameter called rate. For the bias, we have it set here to 5 volts per second. So no matter how fast you change the front panel, it will never move faster than the 5 volts per second. In addition to being able to set the rate which the bias is changed, you can also set a minimum value that the bias can be set. If you're not being careful and watching the screen when you're lowering the bias voltage, this minimum limit prevents you from setting it to 0 and crashing the tip. I'm sure almost every researcher has done that accidentally. That was something you could do with the SPM 1000 if you weren't looking at the knob and turn it all the way to 0. To allow the R9 to be equally useful for a beginner as well as an advanced user, the R9 allows each control panel to be customized by the user to select which parameters they want to be visible on the dashboard. Let's take the Z feedback loop as an example. There are many parameters that can be made available for use. You can, as shown here, show the set point, the proportional, the integral gain, the tip control, the feedback type, and a variety of other settings. Some customers will want to expose all of them. Some customers will only want to expose the set point in the integral gain. So by simply turning off the controls that aren't used very often, you remove the possibility of setting them accidentally. So for your students that are beginners, you just expose a couple, and as people get more comfortable, you expose more. So you can very easily switch between linear feedback, logarithmic feedback. We have a new divide feedback mode. So any of these can be quickly and easily set. Other users might want to be able to manually freeze the feedback loop, retract the tip, center the tip, or ramp the output to a specific value. These were functions that were not available with the older SPM 1000. So once you have the system set up the way you like it, you can just name a new parameter file. So the user interface will be customized for each student, each user, as they start up the system. Some panels are not needed for every experiment, so the less frequently panels can be quickly hidden from the dashboard. It's just a mouse click away to bring them back. Now, most of the controls will be used from the dashboard. So for starting the scan, stopping the scan, saving data, it's quite intuitive. This is something that most people will learn themselves very, very quickly. I want to point out one particular, what we call the custom tip, just so you can get an understanding that if you want to do something different, something a little unique, how you'd go about doing that. So here we have a panel called custom tip. And what this does is if I put in 2 nanometers and push custom tip, it will retract the tip by 2 nanometers. In the past, with the SPM 1000, you had 2 choices. You could say retract the tip, it would pull it back all the way, which helped protect the tip. But when you released it, now you could have a long-term piezo creep, which showed up as drift in the image. So a lot of people wanted just to be able to retract a small amount. Well, with the SPM 1000, you could say freeze the feedback loop, then use the offset knob to retract back a couple nanometers. Well, that had a set of problems too. If you have any thermal drift in the system and the sample drifts towards the tip, you'd crash the tip. We have a better way in R9. It's just a smarter system. So now I'm going to switch to the IHDL mode and show the procedure for custom tip. When I say a procedure, every time you push a button on the front panel, scan, take IV curve, you're running a procedure. And from the very most simple procedures to the most complicated procedures, they're all made using IHDL with just a handful of icons. These are easy to learn, easy to use, and extremely powerful. A few basic rules. Every procedure will start with the start button, it'll end with the stop button. If you want to do something, you grab and activate and drag it onto here. So once I've dragged on, I click on an activate. What that lets me do, I'll get a drop-down list of every hardware item that's on my hardware space. You know, every DAC, every A to D, every feedback component. So here I'm going to say I want to do something to the Z feedback loop. What do I want to do to the Z feedback loop? I've got a lot of choices. I could change the set point. I could change the gains. I could even change the feedback from linear to logarithmic. Any control that I can make manually, I can have done automatically inside of a program. So once I've selected tip control, I can say I want to freeze it, I want to retract it, I want to center it, I want to ramp it to some value. So here, simply dragging on activate and say pick Z freeze, I've told the system when I push start, first freeze the feedback loop. Next, I need to make a decision. So I grab one of my components that says, if then. This can make a decision. So I have a choice to go inside and read a value. So if I wanted to check the Z position, the tunnel current, any of the electronic signals running around, I can measure. Or as a reference, in this time I'm picking reference, is it's looking on that little panel that I showed you on the front panel where we typed in 2 nanometers. So here it's checking, is 2 nanometers, is that value greater than 0 or less than 0? In the case where it's greater than 0, it follows this path. So I follow this path, I grab another activate. Again, I say activate the ZPI, and I want to retract the ZPI. Now we got different choices. I can either pull it back as a jerk, or I can have it ramp back at some defined state. So I can define either the time it'll take to retract or the rate to which to retract. So here I'm saying whatever value I pulled in, take 50 milliseconds and pull back 2 nanometers. Then I'm done. Now what I've done here, this shows the lower bound. Our feedback loop has both a lower bound and an upper bound. So what you can think of this as is restricting the range of motion of the Z. So what I've done is allowed the tip to go no farther forward than 2 nanometers back from the surface. So it's saying pull back 2 nanometers. You can't go any farther forward, but I'm not restricting it from pulling away. So if there's any thermal drift in the system, the feedback loop is active. So I will not crash into the surface even if I drift more than 2 nanometers. Had the number I put in been a negative number, this would have moved closer to the surface. And again, you can adjust at how fast you want to go. Some people use this for preparing the tip. Instead of just jabbing the surface, you can define how fast you want to ramp in. So this is just a very simple couple-step process that you can optimize the way you want to do things. Now, the configuration that we have here is set up for simple STM that allows me to take topography, IV, DIDV measurements. I have a single lock-in configured. But say I want to measure, say, the second derivative, in addition to the first derivative of the current. We come into our hardware space. I already have one lock-in built into the system. So I simply say, grab another lock-in. Now I take the current signal from the A to D. As I drag, it'll show me this is where I connected to the lock-in. Now, if I want it referenced to the oscillator, the bias modulation, this is the bias modulation. This is its reference out. Now, you have to think of it a little different because this is actually a digital reference out. Where a normal lock-in would be analog, this we can maintain zero noise and a perfect precision. So simply by connecting up, I now have a second lock-in. I come to the dashboard. It automatically brings the controls for that second channel to the dashboard. I can say now I want to look at the second harmonic, and I'm ready to image. That's how easy the R9 is. Imagine how much more work try to set up a second lock-in, an external box, how many BNC cables and how many BNC-Ts would be required to do that. Doing it digitally, internally, adds zero noise. Again, I want to point out that most customers will never need to create a procedure, as most procedures have already been developed and are available for use straight out of the box. But it's good to know that easy customization is just a few mouse clicks away. You can start to work with our IHDL programming language and do things in just a few hours, not the weeks and months or even longer that are required to learn a language such as LabVIEW or C. I'm now going to switch back to the main monitor. I've now explained most of the features and capabilities of the R9. I think that gives you a good flavor. I'm just now going to show a little bit of data that some of our customers have sent to us that have been using the R9. These two images were taken when a new microscope made by Unisoka Company of Japan was installing microscopes for their customers. Unisoka makes very nice cryogenic microscopes, especially for the millikelvin market, and they typically deliver those microscopes with RHK R9s. So as you can see, image 1 and 2 are graphene islands on ruthenium, acquired at liquid nitrogen temperature, where image 3 and 4 are showing the gold reconstruction on gold at liquid helium temperatures. Spectroscopy is one of the really strong capabilities of the R9 and things that make it uniquely suited for spectroscopic measurements. This measurement was actually made by the person that had the very first R9 that we delivered, Dr. Ray Chowdhury at Tata Institute of Fundamental Research. He has a homemade microscope that works down to the millikelvin. He'd originally had an older RHK SPM 1000. He had one of our competitors' microscopes, but he really needed a microscope that would allow him to image these very, very small band gaps, superconductors. Here you can see it's down about just 1 millivolt. Most controllers simply can't see this due to their noise levels. With their old controllers, they needed to use an external lock-in and take many, many curves to average together due to variations from measurement to measurement. With the R9 system, they really had a big improvement because we have some very unique capabilities that we've put into the spectroscopic measurements to allow you to have much more repeatable gaps when you close the feedback loop between each different measurement. For instance, we turn the bias modulation off when you're stabilizing the gap. We turn the feedback loop very slow while you're setting the gap resistance before you freeze the feedback loop. So you can see on the curve, 50 curves were made with very, very little variation between them. You can see we got a very nice comment from Dr. Ray Chowdhury that showed what was the quality of the data that he was getting on the R9. So not only is our built-in lock-in amplifiers provide as good of performance as the best lock-in you can buy, it's much, much easier to use when it's fully integrated. Here's some more spectroscopic measurements that was made by a customer that has both a couple old RHK SPM 1000s as well as some controllers from another controller company. With the other controller company, they were simply not able to measure this small spectroscopic feature due to the high noise levels of the electronics. And particularly problems were the glitches at 0 volts that were showed up on the DACs of our competitor's controller. They simply could not make this measurement with the other controller. With the R9, it was quick and easy. And you can see how Dr. Shi feels about the controller. The performance of the internal PLL is also very high, very easy to use, very little noise, very, very high stability. These were some measurements that we made in-house using the internal PLL of the R9 when we were making some tests with our own UHV AFM, Q+ based. So these data were acquired at RHK on an RHK microscope. Since the system was launched, the RHK R9 has started to really gain speed in sales. We now have over 100 systems that have been developed with quite a few more on order. Here's a partial list of people in the US, Europe, in Asia, and other parts of the world. You notice how many groups have bought multiple controllers. They usually buy one, and when they like it, they buy more. I've shown you many of the unique features and capabilities of the R9. When buying a controller, it's important that the controller must not only meet your immediate requirements, but also be able to meet the requirements of future unknown experiments. You know what this system needs to do today. You can write a specification that tells how many channels of data, speeds, noise levels. and that'll probably last you through the next grad student. But this controller should last you a generation. We have many RHK control systems that are out there 10, 15, even more years old. So you really need to make sure you have a controller that meets not only today's needs, but those of tomorrow. And how can you guarantee that? First of all, the R9 contains so many A to Ds and D to As, it'd be difficult to imagine an experiment that has more hardware requirements than what the R9 contains. The noise level is so low and the data accuracy speed is so high, again, this certainly exceeds the needs of most current experiments and likely will meet your requirements for many years to come. The regular firmware updates, most of the magic of the R9 takes place in the very sophisticated firmware inside of the FPGA. With the SPM 1000, if we wanted to change something, we had to change a circuit board. If you wanted to change things, you were there with soldering iron and wire cutters and trying to put in new components. Here we can continually upgrade the capabilities simply by sending you a file that you download into the R9. The existing R9 has one PLL and one lock-in. Our next firmware release that you're going to get for free will add a second PLL and 4 more lock-ins. Imagine getting a PLL and 4 lock-ins of the high performance of RHK simply by a software upgrade. And those are just things that we've done in the last 6 months. As customers' needs evolve, as we get more involved in our near-field optics, adding more and more sophisticated capabilities, these are things you're going to get for free. This is as future-proof of an investment as you can possibly make. We've also added significantly more LabVIEW and MATLAB integration. We've had customers that want to integrate the R9 into larger systems to interface with the spectrometer, with magnets, with lasers. So now you can control the R9 through an external interface such as LabVIEW or MATLAB. So you can turn on a magnet, turn on a laser, then tell R9, take an image. When it's done, it handshakes back to your program, lets your program change any operating parameter in the R9, scan size, bias voltage, frequencies, tip position, and then tell it to take another scan. These are things that are fast and easy to do. That's the end of the presentation. I'll now look to see if we have any questions. I don't have any questions from anyone. I can't possibly explain things that well. So if anybody has any questions, please type them in. One thing I want to make sure that everyone knows is that we have a very generous trade-in policy for older controllers. To give sort of our thanks and appreciation for being a previous RH customer, we offer quite a generous trade-in for RHK controllers of any age. For a controller in the last 5 years or so, we can offer quite a nice trade-in value because we have a waiting list of people that want to buy used SPM 1000s. Many people simply don't have the budget for a new control system, and their needs might be more modest. We even take in trade-ins of older controllers for our competitors. As you exit the webinar, there'll be a brief survey that I appreciate if you could take. Just a few questions. Did I explain things well? Did you learn anything? Do you have any questions? Would you like us to contact you? We'd appreciate if you take time to fill that out. Well, I thank everyone for their time. I hit my 1 hour more accurate than I normally do. So this is, we all at RHK appreciate the time for listening about our R9. Thank you.